also the same. Any bid that a bidder makes, say I am talking in terms of B1, any bid that a bidder makes, he subjects himself to a lottery. He might win the auction or he might lose the auction. If he wins the auction, his payoff will be B1 minus B1. If he loses the auction, his payoff will be 0. Therefore, all I need to do is to find the probability that he will win the auction and the probability that he will lose the auction. Okay? Now, after that, you know that I'll multiply this probability value with this, that will give me plus the probability value with this, that will give me the expected payoff of bidding B1. So now, let me write down my expected payoff function. The expected payoff to bidder 1 of his bidding B1 when the other guys are bidding B2, B3, Bn. Remember, this is a game. My payoff depends not only on what I do, but what the other guys do. Okay, once you keep the terminology in mind, once you are very clear about why you are writing this, things become a lot simpler for you conceptually. Okay? So the expected payoff to bidder 1 of this is simply the probability that I will win with that bid times B1 minus B1. This will give you a 0, so I am ignoring that. Now, what is the probability that I will win? And the answer remains the same. So well, you will only win if your bid is the highest amongst all n bids. Now we have n bidders, there will be n bids. As long as your bid is the highest of all n bids, you will win. What does that mean in mathematical terms? That's in English. If you convert that to mathematics, probability of winning is probability my bid is greater than the second player's bid, and my bid is greater than the third player's bid, and my bid is greater than the fourth player's bid, and my bid is greater than the nth player. That's what it means. That's what it means. And of course, I still have my payoff here, B1 minus. That's what. Notice I have a very complex looking expression here. I want to simplify this in some way. How do I simplify it? I use the assumption that I made in my first lecture on auctions, that bidders' valuations are independent of each other. Independent of each other. That means if I draw one bidder from that distribution, the valuation he will have has got nothing to do with if I draw another bidder from it. And you will recall elementary statistics, stats 101, that probability of A and B, if A and B are independent events, is just a multiplication of the probability. So, if bidders' valuations are independent, bidders' bids will also be independent. Therefore, whether my bid is greater than bidder 2's bid is independent of whether my bid is greater than bidder 3's bid, or bidder 4's bid, or bidder n. That allows me to break down this complex looking inequality into simpler terms. Probability B1 greater than B2 times A and B, probability A times probability B. B1 greater than B3 times probability B1 greater than Bn. Nothing can change to the payoff from winning. We still have B1 minus B1 here. Okay. Now, okay, all I needed was to break it down into simpler pieces like this, and now I can focus on each individual term here and ask myself, what value will that take? Remember, after I get this expression, my job will still be the same. I will differentiate this function with respect to B1, set it equal to 0 and solve for B1 star. Therefore, I need expressions for this. I need expressions for this, functions for this. Otherwise, I can't differentiate. I need functions for this. Okay? Functions. The only way to get these functions is to go back to a uniform distribution of valuation. To do that, I must use my beliefs first. Discussion? To do that, I must first use my belief about what other bidders are doing. This is the step where you replace B2s, B3s, and Bns with your belief about what other bidders are doing. Why do you do that? Because you've got to use this uniform distribution. This is a distribution terms of valuation. Somehow you have to get valuations into the picture. Somehow. Otherwise there is no way you can do it. That is why it is important to notice this is the distribution of bidders' valuations, not of their bids. Okay, not of their bids. Alright. So what did we assume? We said that unless otherwise stated, every bidder assumes in a first price auction that every other bidder is bidding a fraction of his valuation. This is our belief all the time. Okay, no point bidding your valuation, therefore you will bid slightly lower. Every bidder bids a fraction of his valuation. That allows me to substitute D2, D3 and Dn with the respective valuations of the bidders. So B1 greater than FB2 times probability B1 greater than FB3 times probability B1 greater than FBn. Of course, your payoff still remains B1 minus. Okay? Or next step. I've got a valuation in there. I got a valuation in here. Therefore, I can think of using that uniform distribution to find functions for these values. But to do that, I have to first rewrite this inequality. That is an argument of this probability function. I have to rewrite this inequality with B2 and the Bn and the B3 as the subject of the formula. How do I do that? Very simple. So making the subject of the formula, you get this. Probability B2 less than B1 over F times probability B3 less than B1 over F, probability Bn less than. Got it. And we still have B1 minus. Okay? Alright, ready? So all of these terms are B1 over F. I am trying to find what is the probability that a randomly drawn fella, bidder 2, has a valuation less than this. And clearly, that is the ratio of this line segment to this line segment. This line segment is B1 over F, this segment is 1, therefore this probability is B1 over F over 1, which is B1 over F. Look at this. What is the probability that another randomly drawn bidder has a valuation less than B1 over F? Same thing. Bidders' valuations are independent of each other. Therefore, the probability that the second bidder has a valuation less than B1 over F will be the probability that the third bidder has a valuation less than B1 over F. What is the probability that if I draw the third bidder, his valuation will be here? This line segment over this line segment, which is B1 over F. What is the probability that the nth bidder will have a valuation less than B1 over F? Also. We'll have our payoff. Notice how many terms are there here? There are n minus 1 B1 over F terms because we start from B2, not from B1, right? B2. Second bidder, third bidder, nth bidder. Therefore, there are n minus 1 B1 over F terms here. Okay? Now use that, you will get B1 over F to the power n minus 1 B1 minus B1. God. This is the expected payoff, ladies and gentlemen, to any bidder, in our case bidder 1, of bidding B1 when other bidders are using a linear bidding strategy, bidding a fraction of their valuation. Okay? Alright. What is my next step? My next step is to differentiate this expected payoff function with respect to B1, set it equal to 0, and solve for B1 star. Let me do that. So E phi 1